Hello and welcome to my next presentation, which is called Cool Comfort Passive House for the Hot Season. Here I want to address the question that I always get is, can we keep cool in a passive house? We probably all understand that passive house can keep us warm. Yeah, so it comes from a cool climate, but can it keep us cool as well? So this is what I want to answer today. And for that, I want to share my little presentation. Good. Welcome to the presentation, Cool Comfort Passive House for the Hot Season. And firstly, I want to address a very burning question with you. And the burning question is it possible to build a passive house in a hot climate? Yeah, so that's a question I get asked a lot because after all, passive house originated in Germany, where we have a cool temperate climate, right? So we all understand that that works for there, but can we build passive house in a hot climate as well? For that, to answer that, I want to ask you to imagine something. So I want to ask you to imagine that it is summer, you're at the beach, and you're having a relaxed lunch with family and friends. Because it's hot, you want to bring some cool beverages. Okay, so that's the scenario that I want you to imagine. So for that scenario, would you rather take an esky or a cardboard box for your drinks? Yeah, so picture that. What would you take to the beach on a hot day for your drinks? Also, what would you do if you have said, I'd rather take the esky? Then that's probably the clever answer. So you're taking your esky. And would you ask everyone to close the lid again after taking a beverage? You probably would, yes, because if the lid is left open and all that hot air would come inside your esky, and that wouldn't be very helpful for your cool drinks. The other question I would ask you is, would you put that esky in the sun or in the shade? Yeah, so you probably say, yeah, of course I would put it in the shade because that way my drinks are staying the coldest for the longest duration. Yeah. So this is now a little metaphor, a little picture that hopefully gets you to understand what is happening here. So back to our initial question, is it possible to build a passive house in a hot climate? For that, we have to say, yes, it is, because the heat doesn't know the difference between inside and outside. Yeah. So we're taking our esky to the beach to keep something cold inside. And that's exactly what passive house can do. We can keep cold inside because we're separating the two environments, yeah, the inside from the outside, and the heat doesn't know where inside and outside is. We're just separating it from a heat transfer, yeah, and that's what our esky is doing, and that's how we can translate our findings now onto a building, okay? So we can apply those findings from the esky to our houses. We want to separate the indoor environment from the outdoor environment. How do we do that? We do that with good insulation, just like our esky, yeah, it has a thick layer of insulation. This is usually a foam or something like that. In our houses, obviously, you can use different materials. We want to make it airtight. Yeah, we want to close the lid so that the hot air is not coming in. We want to close the gaps in our thermal envelope so that no hot air is coming in. And we want to have, obviously, also passive house windows, which is part of our thermal insulation layer that form that part of that insulation, that separation between the inside and the outside. Additionally, I asked you for putting it in the sun or in the shade. We want to apply some of those passive cooling measures as well, like adequate shading. I will talk a little bit more about some other passive cooling measures that we can apply in our passive house. And if overheating is still an issue after all of these measures, then we can introduce some active cooling like a split system aircon. And that's how we can keep cool in our passive house, but we've got a lot of options to stay cool without even touching the active cooling component. And we want to talk about that now, why that helps us stay cool in a passive house. So the first thing I want to address is these passive house components that I've mentioned up here, our passive house components. And the first one here is thermal insulation. Yeah, so that's probably the biggest one to keep us cool. So thermal insulation reduces transmission of heat. Yeah, so it's a material with a low heat transport, so with a low conductivity, that's used to shield a volume against the gains or loss of heat. So here we're saying gains or loss because now we're applying that to either a hot or cold situation. So you see that already. The thermal insulation protects against a different temperature, and that works in winter as well as in summer, like we've just learned, yeah? So we can protect against that different temperature no matter where the hot side is, because heat doesn't know the difference between inside and outside. We're just protecting here against the transport of heat, the transmission of heat, and we can do that in a warm situation as well. So now I want to go a little bit into why thermal insulation works. Yeah, so why does it work? And the question is it the material that thermally insulates? And to that we have to say, no, it's not the material, but it's the small air or gas pockets within that material. Yeah, so the pockets have to be small enough that there's no air or gas movement. So we don't want any convection. So convection means gas movement or air movement. So none of this. And then we can talk about a thermally insulating material. So think about all the materials that you typically would use for thermal insulation. It would be a fluffy mineral wool. It would be a foam that has a lot of air bubbles in it. So anything that has air in it is good for insulating. It's a little bit like your woolen jumper on a cold winter night, or like your esky on the beach, where that esky has this foam around it that also is full of air bubbles. Now with that, talking about those air bubbles, I want to say, why does this thermal insulation perform? We've just said that because we don't have this air movement. Yeah, so air movement always means heat transport. So air transports heat from one side to the other, depending on which side is warmer now. So what we need to do, we need to isolate that. We need to stop that air movement. So thermal insulation has air pockets where the air can't move. So only when we have inclusion of air that's protected against air movement, that insulates. And that brings us to our second part, which is our air tightness. Do you remember how I said close that lid? That's a little bit different because here it's going through a gap, not through the actual insulation itself, but that's what we want to do. We want to stop the air from going to any gaps and cracks, and we want to stop the air from going through the insulation as well. So our air tightness is really important to isolate the indoor environment from the outdoor environment from any air movement. That also protects us from hot air coming into our interiors. So you could imagine if you had a very well protected home, but you had a gap somewhere or a crack somewhere, or you left the window open a little bit, all that hot air would come in, and that's why we need air tightness as well. Then I talked a little bit about windows. Okay, so windows are a big part of the thermal envelope, and they need to perform as well. And how do windows perform, or how does glazing perform? So if we're looking at a single pane of glass with or without foil or coating, that's doesn't matter, it's not sufficient. It doesn't perform, yeah? A single pane of glass doesn't perform because the temperature can just permeate through. Glass is a very good thermal conductor, so it conducts heat very easily from one side to the other. You would have probably experienced that if you had a glass mug and you put some hot beverage in it, you would burn your hands really easily because glass transports that heat really easily. What would you do? You would probably use a double-walled glass where we now have that layer of air in between the two layers of glass, yeah? And that's exactly what we're doing here with the window. What makes the difference? It's the air pocket with still air in between. That makes the big difference, and that makes it now so that it can insulate. All right. Now we talked about some of the Passivhaus components. It's not all of them, but these are the main ones that keep us separated from the indoor environment, from the outdoor environment, that keeps us cool. And what does Passivhaus achieve with that? Yeah, what does Passivhaus achieve with such a good thermal envelope? And for that, I want to show you this little picture. So we have here our Passivhaus where we have inside our thermal comfort zone between 20 and 25 degrees. That's what we want to achieve. So obviously on the warm side, so when it's summer, we are staying here at the maximum of 25 degrees. That's what we want to achieve. And for that, Passivhaus on the hot side allows 10 watts per square meter to go through our thermal envelope. Yeah, so that's the limit that Passivhaus has set. 10 watts per square meter can go through that thermal envelope. That's what we're allowed to let in. And that's what we need to then get rid of on the inside, that 10 watts per square meter. And this 10 watts per square meter is allowed in Perth. You're allowed to do that in Sydney. You're allowed to do that in Germany. And you're allowed to do that in I don't know, in a very hot country, I don't know, somewhere in the desert, yeah? It's always the 10 watts per square meter. It's also the 10 watts per square meter we're allowed to let out in a winter scenario, yeah? So on the cold side, we're allowed to let 10 watts per square meter through our thermal envelope, and that also doesn't matter whether you are in Antarctica or whether you are in Tasmania or whether you live in Melbourne. It's always the 10 watts per square meter. What does that mean now for our thermal envelope? If it's always the same amount of energy that we're allowed in and out, it means that we have to adjust our thermal envelope to the climate condition that we live in. So what means that in a harsher climate, we need a thicker buildup to protect us from that heat, or we need a thinner buildup in a milder climate to protect us from that heat. Yeah, so the buildup changes, the amount of energy we are allowed to let through stays the same as per the definition of the Passivhaus standard. Yeah, and for that, we could now look at our thermal differences. What is the thermal difference? It's the difference between our indoor temperature, so our thermal comfort range of 20 to 25 degrees, and our outdoor temperature, where we have extremes on the high and on the low. And now let's have a look what happens in the different climate zones. Okay, so we have a thermal comfort of 20 to 25 degrees. If we live in a climate where we have the highest extreme of 45, then we have here a temperature difference to the hot side of 20 Kelvin. Okay, Kelvin is another word of expressing a temperature, or in other words, I always talk about Kelvin when I talk about a temperature difference. Yeah, so it means 20 degrees. Yeah, so that between 25 and 45 is 20 degrees difference, 20 Kelvin. I say 20 Kelvin. And then on the lowest side, so if we live in a climate, that would probably be a typical Sydney or Perth climate, something like that, so relatively mild. So on the lowest extreme, we have about 0 degrees, and so we have a temperature difference of 20 Kelvin as well. So we see now on both sides, we have the same temperature difference. So now we have to build our buildup so that it can withstand that 20 Kelvin difference. Yeah. If we live in a more extreme climate, so let's say this would probably be a European, German climate where we get up to 40. So these days they get up to 40 degrees. So now our hot extreme is only 15 Kelvin. Our cold extreme could go down to minus 20 degrees, so 40 Kelvin difference. So now this is dominant. So now we would have to build our building envelope so that it can withstand the 40 Kelvin difference. Yeah, so really thick now. And you can see that this temperature zone would already be super protected for the hot climate. Yeah, so they wouldn't have a problem in summer because their protection layer is so thick already because they've prepared for the winter. Now they're really well prepared for the summer as well. And then we could have the other extreme where we maybe have a very hot climate where our highest extreme is higher. So our highest difference here is 25 Kelvin, and maybe it only goes down to 10 degrees. So now we need to adjust our thickness of our thermal envelope to this highest degree extreme here on the hot side. So we always want to do that and want to be protected against the highest extreme that we have, the highest temperature difference. Yeah, and that's what Passivhaus is doing. We are now adjusting with those measures that I said, thermal insulation, air tightness, windows. We want to be protected against the highest extreme in our climate. Good, but now I want to come to cooling measures. So because this is the one side, so our thermal envelope protects us from the heat coming in the first place, but obviously we have to, or we can also introduce some other measures, some passive cooling measures. I've already mentioned one of them. It's the shading. So I want to talk about a few of those in here as well, because that's the first thing you can do in your Passivhaus to make sure that we are staying the coolest for the longest time, yeah, and without any additional energy that we need to spend on our Passivhauses. Okay, so the first really important one is our shading. Yeah, shading, we probably know that because we've grown up in a warm climate. So shading principles are where we're saying that, yes, whilst we want this sun into our building in winter, we really want to be avoiding them in summer. And the sun protection should not block natural light permanently, but we want to have a proper shading so that we're not getting the heat in, and we want some glare protection as well. So how effective, or when is our shading the most effective? So what we don't want is we don't want the shading object to create a subclimate between the glazing and the shading object, and then it works best. So a good example could be a mountain in the distance, another building, trees, because there is enough air movement between that object and your glazing. But if we have another shading object that we are designing onto our building, obviously these are things that we often can't influence. So if we're creating a shading object that creates a higher temperature on the glazing surface, then the shading benefit could be reduced. So an external blind, even roof overhangs sometimes could have that negative effect. I want to show you what I mean in the next slide here. So the effectiveness of shading is reduced by producing this heat pocket here. Yeah, so here we have a blind on the frame. Shading devices should always be on the outside. Remember that as well. A shading device on the inside, like a curtain or a honeycomb blind or something, doesn't have the same effect because the heat is already in your building envelope. Yeah, so if you want to shade it from the inside, the heat is already inside, that energy is already inside. We're just delaying it a little bit to come into the interior. So shading needs to be on the outside. Glare protection can be on the inside. So you want to have your shading on the outside. What happens here is that we're creating a heat pocket with not much air movement. And that air temperature in this pocket can be now around 60 degrees. So now that 60 degrees will come through your glazing inside instead of the whatever 35, 40 degrees that the ambient temperature is. The same could still happen with a blind on the facade. Here is a little bit of air movement, so a little bit better, but the temperatures can still be high. So ideally, you want to have a shading device that looks like this, where we have no air movement restriction, and where this air out here is the closest or close to the ambient temperature if it's in the shade. Yeah, so that's your best bet for your shading. Then there's different shading types. So obviously, as I said already, we can have a site condition that gives us shading, like mountains, building structures, and trees. Often we can't influence them. So be a little bit careful. If it's a building or a tree that could be removed, then have a think about what would happen if that's removed and if you need to replace that shading situation. Then we can have fixed devices like fixed blinds, balconies, verandas, things like that can work really well. They obviously are a little bit less prone to failure or to wrong usage, but we have to make sure that we can still get that sun in when we want it in winter. For the low sun, we actually want that sun inside to help us with the heating, but for the summer, this could be a good option. And then we have movable devices like movable blinds, shutters, and shading cells. They're a good option because they give the user a little bit more flexibility to move it, but also there is then the risk of user error, obviously. But maybe a combination of those would be the right thing to do. Good, so that's one thing. Shading is our one-act passive cooling measure. Then the next thing is ventilation, window ventilation, yeah? So what we say and what we've learned in the course, for those of you who have already done the course, or for those of you that haven't, I'll tell you in really quickly. Windows are usually not sufficient for ventilation. For the amount of fresh air we need into a building, window ventilation is not sufficient because there's not always enough air exchange happening. Yeah, so air exchange only happens when we have a pressure difference. That only happens if we have a different temperature outside or wind or a height difference. Yeah, and some days that's just not given. So for our fresh air demand, window ventilation is not sufficient, but opening the windows for night purging on a cool night after a hot day, that can be a very valuable support for the cooling system. Yeah, so that's still good to open your windows when your outside condition is in favor of your inside condition. And that happens often when we had a hot day, it cools down nicely at night, and then we could open all our windows. So it's a really good support for our cooling system. It's not ventilation. So remember, there's two different things. Ventilation is for fresh air demand, the amount of fresh air we need. And night purging, that's our support for our conditioning system. So we need to separate that. I could talk about that a lot more. As you can see, if you want to learn more, then one of our courses would definitely be a support for that, where we talk about ventilation and conditioning and what the difference is between those two. Now, I quickly want to also talk about thermal mass in a passive house, because that's often something that people value as very important in their homes. But I must say that thermal mass is only a storage capacity. Yeah, so the heat is already in the building, and we can now, with the thermal mass, absorb the heat, and the temperature of the air doesn't rise as much and as quickly as without it. So it does have a little bit of an effect, but Thermal mass needs a significant thermal difference to have a noticeable effect. And in a passive house, our temperature is always constant anyway, between 20 and 25 degrees. So this is not significant enough to make a big difference. You'll probably feel a little bit, but it's not significant. It wouldn't make a big difference. So thermal mass in a passive house isn't a big design element. If you have it, it's okay, but you don't have to go out of the way to put thermal mass into your building. It doesn't have a big effect. The other thing is that thermal mass is not forgiving to user errors. Yeah. So imagine this now. We're here on our Christmas lunch, on our summer lunch, and we're outside on our balcony, on our terrace, and the people are leaving the doors open all day. Yeah, it's 40 degrees outside, and everyone's going in and out. The doors are left open. Now all the heat is coming into your building, and the thermal mass would now absorb all that heat. Then the people are gone in the evening, you close your doors, and you're thinking, finally it's nice and cool. But now that thermal mass has absorbed all that heat and will release it into the building, and now the building is hotter than it would be without the thermal mass, and you need extra energy to cool that down again, to get rid of that heat that's stored in the thermal mass. It works the other way as well. If the doors and windows are left open in winter and the heat escapes, then you need more energy to heat it up again. Okay, so thermal mass could also work against you. So be a little bit careful with thermal mass. It's certainly not something that you have to have in your passive house. It's okay to have it, but it's not a major design element. And then the last passive measure I want to talk to you about is cool roofs and reflective colors. I think there's been a lot of discussion about this going on, especially with councils. They're sort of promoting this a lot. And if cooling is an issue and heating demand is low, then cool roofs and reflective colors make sense. Please make sure that your issue isn't created by an unshaded glazing or an unshaded facade, because that often is the case, that we have overheating, and the problem is not really the roof or the color of the roof, but it's somewhere where we haven't put proper shading in for our windows. So if that's not the case, then it makes sense to have these cool roofs and reflective colors. So make sure that your solar reflectance is bigger than 0.7 and your thermal emittance bigger than 0.75. This can all be entered into the PHPP, which is our passive house planning package. That's our software for certifying passive houses, and it can be entered in there. Good. So after all this, we've learned about the components that keep us cool. We've learned about passive cooling measures that keep us cool. We could now design our passive house with no conditioning. Yeah, so we could say we don't need an active conditioning system. We're sure that our passive house withstands the heat. And passive house also allows in the standard a overheating of 10% of the time over 25 degrees. So passive house standard, I've got a little bit of an extract here. It's not the full standard, but I wanted to show you we're allowed to use a certain amount of energy for heating and for cooling. But we could also say we don't want to have use energy for cooling. We want to have no cooling system in our building. And then we allow 10% of the time over 25 degrees. Yeah, so that's what I wanted to point out. Now the question is that bad? Yeah, so now we're saying we're allowed to have overheating in our home. Is that bad? Is that some people say, well, passive houses are overheating. Yes, they're overheating by design, by the looks of it, but how bad is that? And it depends how much this overheating is. Yeah, we are not saying, the standard doesn't say how much the overheating can be. It just says over 25 degrees. And what we should do when we're doing our design is we should do a cross-check in PHPP, and that can give us a good indication of how bad this situation would be if you're not using active cooling measures. Yeah, and for that, I want to show you a little something that we've put together from Smart Bus Academy, a spa special, where we're saying we can test our temperatures in our passive house with PHPP. The way we would do is we would adjust our comfort zone. For those of you that haven't used PHPP yet, don't worry, once you go into PHPP, you would understand. So you can adjust your comfort zone temperature. And now you could say, okay, at 25 degrees, we have 10% overheating. We can't define if that's good or not. Yeah, because this overheating could be, if that would be up to 33 degrees, then that's not good at all. You don't want to sit in a home where it's 32 degrees. So now you could adjust your comfort zone to 27 and see how much overheating we have at 27 degrees. And if that's 0%, then it's excellent, because it means that all your overheating happens between 25 and 27 degrees. So your overheating is only up to 26 degrees. And I think we can all live with 26 instead of 25 degrees. Then if we have at 27 degrees, 1% of overheating, then it's still good. If it goes up to 28 degrees, then it's acceptable. Once we're hitting 29, 30, it's poor or terrible. Yeah, we don't want to have in the home a temperature that's higher than 29 degrees. And that's how we can test it. And that's a very good measure. We're saying that even if we have 20% overheating at 26 degrees, we would have an excellent outcome. Yeah, because then it's just a little bit warmer, but we need to see how high that overheating is. And that's what the Passivhaus standard unfortunately doesn't define, but that's something that we are saying you should definitely do for your client so that you're creating a comfortable, cool indoor environment. Good, so that's designing with no conditioning. If you're saying, look, in my case, we still have overheating at 30 degrees. We can't just do it with our Passivhaus components and our passive cooling measures. We need some active cooling measures. Then that can be done. Yeah, so active cooling measures can always be implemented then if you're saying that, yes, we would have too much overheating or we just want that little bit of extra comfort. Now, the question is overheating an issue? Yeah, and we're saying that cooling is only needed when the sun is shining. Yeah, what makes it hot is the sun. The sun is out there when the cooling is needed. And then our PV, our solar system can create energy. So cooling is not an issue, and building in hot climates is easier than in cold climates. Yeah, so because cooling can be cheap, but heating is expensive when we're looking at an economy where we want to use a renewable energy. And I show you a little graph why cooling is cheap, and to explain why cooling is cheap and heating is more expensive. This is a graph where we're looking at sustainable energy. So we're looking at wind, water, and solar. So this is the amount that's produced. And the problem is that, so we can use some of it directly. That's ideal because we have the least losses. So if we're using our solar direct from the roof and we're using it to cool or to run our fridge or whatever, that's the best because we don't have to store it. If we have to start storing it, then we're always having losses. And that's the problem. So if we're having a summer situation where we only need a short-term storage, so let's say there's enough energy during the day, we just need to store it into the night, then we have a pretty good efficiency for storing it. Short-term storage is already pretty good. We have 80% efficiency. But if we say we need to now store it from one season into the next, so from summer into winter, then we're having a lot of losses. Yeah, so here this is a chemical storage. I don't want to go too deep into that, but here we only have 30% efficiency. So 70% of that energy that we're producing is getting lost in that process of storing it. Yeah, and that's why heating will be a lot more expensive in the future if we're only looking at sustainable energy, unless we're finding some kind of solution where to store it cheaper and without so many losses. Yeah, so that's why we're saying cooling is not a problem. Cooling is there when the sun is shining and we have that energy available. And the best thing to do then is we could condition with a split system. That's the easiest, most often the easiest and most economical approach. There's other options, cooling surfaces, chilled ceilings, things like that, but all of them are a little bit more complicated. This is the easiest approach. Obviously, they're not the prettiest, but they could be hidden in bulkheads or a cabinet. So if you are an architect listening here, that's then up to you or to the designer to make that nice, hide it in a wardrobe, in a bulkhead, so not to be so visible. And the problems that we could have, so maybe I'll explain that picture a little bit more. So this HRV duct, that is our fresh air supply. Yeah, that's not conditioning. That's just the fresh air coming in. And our split system would do our conditioning. In other words, this would remove the heat that we have excessively in our room. Obviously, with split systems, because it moves a lot of air around, drafts can be an issue. Yeah, because we have recirculated air. But the beauty with Passivhaus is that we can condition our building at any time. We're not time dependent because Passivhauses hold temperature for a long time. We've just talked about that thermal protection. And so if we're cooling our building, let's say you cool it in the afternoon at 3 o'clock for half an hour, and then your building is nice and cool. When you come home at 5 o'clock, your building is nice and cool. You don't have to run the split system while you're at home. Yeah, you can run it when the PV is giving you the most energy, run it then, and the passive house is keeping that coolness inside. Not like a leaky home where once you turn the aircon off, all that coolness is gone again through all the gaps and cracks and the non-existent thermal insulation. That's the beauty about passive house. We can now cool whenever we think it's right, and it will keep that coolness for at least 24 hours, obviously depending on what's happening outside. Good, so that concludes the presentation about Cool Comfort. So thank you very much for listening to me. I hope this all made sense and it explained a little bit how we can keep cool in our passive houses with our passive house components, our passive cooling measures, and if we need it with our active cooling measures. So thank you very much for listening to me, and I'll see you in my next post.